Hi everyone, good evening, good morning. Today we are going to be going over this paper called Titans, Learning to Memorize at Test Time. This is one of the, I would say, very, very important paper. Just released, came out a few weeks back. If you look at that, it's actually on December 31st, 24. It's just a few weeks old. It's already making a lot of news and noise. And so many people are trying to provide commentary. And then if you go to YouTube, you can see there are many sort of introduction to this paper is going along. So what we'll do today, we'll talk about this paper, what's the important message from this paper, and I will walk through the key points from this paper, and also, I will give my own perspective as we go in terms of additional information that's not in the paper. I will provide as an explanation. So the objective of today, right after this session, if you go back and read the paper, hopefully you'll get to know more about this area, right? That's kind of the objective. So what this is a paper about? Uh, this is a paper on how the large language model today, as we know, ChatGPT, Gemini, and a lot of these models. Now, what are the limitations in terms of the context window they are handling? How, what are the new ideas in this paper that can help to sort of improve that issues seen in today's, in the LLMs. It's kind of limitations. Um, so if you know, if you play with the ChatGPT and then Gemini and other, mostly ChatGPT, you probably would have noticed in a scenario where you upload a large document. You can, for example, you can upload a PDF in your chat window, and then if you start asking questions, after a while, you would see that the answers are not very good, right? It may give a wrong answer. It may not give them accurate data points. So you will start seeing all those kind of issues, which we call hallucinations, right? These hallucinations happens mainly because some of the models that you have, ChatGPT, they are not able to handle the large context window. So they forget, a lot of information, that is in the past, that means in the window, context window, which is too large. So that's a problem. If you're trying to do a lot of automation, a lot of summarization, and think with a large context, you send it to the LLM, right? So how do we solve the problem? So in terms of the numbers, you may know that a lot of these ChatGPT is 128K token. They say the context window is 128K size, right? That means anything their context window. We will talk about the little bit internals of the transformer architecture, to set the problem, and then why these limitations are there today, and then how this paper is proposing an ideas to solve that problem, right? So it starts with if you look at the paper. So the way I'm going to go through the paper, I highlighted some of the key messages. I will talk about those things. And again, as we go, I will provide my perspective. And also, I have some visual aid wherever it is needed. I have some slides, which is a kind of a visual aid for uh, some of the topics in the paper. Like any paper reading, if the way we should probably approach, obviously look at the abstract, and then once you understand the abstract, then we kind of scan the document or research paper and look at the conclusion, or at the end of the end of the paper, right? What they say, so we get an idea. Um, so just to say that at the end of the paper, what they are trying to say is, this new idea of this. Actually, it is going to be a groundbreaking idea, in my opinion. As we know, you may be familiar with the paper, All You Need Attention, right? It was released sometime in 2017, I guess. Google released that. Now, since that paper, the ChatGPT, right? OpenAI took that and then, able to come up with the ChatGPT. So similarly, who knows, this paper may be a groundbreaking paper, and then the future LLMs, where it can use a lot of these ideas from this paper, and then improve the context window, by which a context window and its ability to reason from the memory, through which we can solve bigger problems and then eliminate the hallucinations or reduce the hallucinations for these large context situations. So what they say is we show that the neural memory, what the key idea behind the paper is, they are going to introduce something called neural memory. Now, what is a neural memory? Neural memory is an additional layer they are going to propose in that paper as a key component which remembers the long-term memory. See, what they are trying to do is they are trying to, sort of look at the human, how we remember, how we make decisions. If you look at the way we make some decisions, we usually we call, we kind of say that we have a working memory, and then we short-term memory, and then long-term memory. So any decisions or any thoughts we have, which starts from our current signals or current inputs, is in the working memory, right? And then we try to get the data from the long-term memory. I'm talking as a human. And then we kind of synthesize the long-term information coming from our long-term memory along with the current information we are dealing with. And then we kind of make a decision. So the current ChatGPT doesn't have that, or the current LLMs don't have that sort of the idea of short term plus long term, and then ability to abstract the information from long term memory and then make a decision or reasoning along with the short term memory. The current LLMs don't have that. All right. So the idea is to see how we can mimic the human way of reasoning from the short term and the long term memory. So that's a key idea behind the paper. How they do it is there, a lot of mechanisms coming in the paper. So just to say, finish that thought, if you read here, we argued that the attention due to its limited context. Basically, what they're saying, well, neural memory, all this are pointing out is, they are trying to convey that neural memory has advantage being a long-term memory. That's sort of the message from these sentences. Okay, so we are going to go more in detail, but if you look at the last statement here, they further can effectively scale to larger than 2 million context window. I think the whole idea is to say that if you go with these ideas proposed in this paper, we can eventually support more than 2 million context window in the LLM side. So that's a claim of this paper. So now a little bit of introduction to, in order to go deeper into that, first we need to get introduced to some concepts. So the next two section, introduction, and then I would even go down, and then preliminaries, are about a little bit history, the way I was trying to convey, and then a little bit of some math behind that. We'll go over that both, and then that sets the context of actually explaining the foundations and components of the proposed system. So, well, we all know about, if you are familiar with the transformer architecture, I'm sure, there are a lot of previous, if you're not familiar, you are welcome to look at the support vector videos that in the YouTube. It has a lot of information about the transformer architecture. Asif has presented, and others also presented, I think, sessions and then meetups on the transformers architecture. And it all starts with what we call recurrent RNNs. So the foundation of new ideas explained in this paper has the origin of what we call RNNs and a little bit of LSTMs. And then it then evolved into something called long memory module, LMM. So, we are talking about how do we design the longer term memory, right? When you think about the longer term memory, what we call long memory, the past memory in our mind, we don't remember all the events in the past, right? For example, if you go back to your own life, you might be remembering, for example, the abstract or summary version of the events happened many years back. It is stored in our long memory, right? And but we don't know all the details, but we know the essence of what happened, many years back. That is stored in our long memory, right? And then how do we design that? One of the goal here is to design that here in this new system. When you think about the two important characters of long memory, so one, we should have the ability. The memory is limited, right? It's limited by its neurons or by its size. Um, so we should have the capability to abstract the information coming constantly to to the system. That's one of the important capability, right? Feature. And the other one is there should be a mechanism to forget things that's not important anymore. So these two things, or actually three things, the limited or fixed memory, right? And then ability to summarize and abstract, and then ability to forget things. All the three things are very key features of the long-term memory. I mean, I think that's true for a human. I think so, as well as in the new system we are developing for LLMs. On the other hand, short-term memory, need not be storing any facts for a longer time, right? It can have the ability to quickly get the facts from the current window, or you can say, for example, whatever happening now, or whatever happening recently, and then it's able to you know add more information from the long-term memory and make some and then decisions in the human. In the case of LLMs, make some reasoning. So the foundation is what we call, in order to design the long-term memory in this context, in this paper, we need to know a little bit about RNN and LSTM. So I will go through that quickly. Though in the paper they are not going through that, I think some of us want to be a little bit familiar with that, so that when we look at the paper further down in the detail, it will help all of us. So I will go through a few slides here, and then I will jump into the I think introduction, and then other topics here. So first, let me show some slides as an introduction. So RNN is a recurrent neural network. It's a neural type of a neural network, right? It has a recurrent in the sense that the output of this neural module or neural network or neural component, you can say, or neurons, is actually fed into the input again. So that's called recurrence, right? And then it also has a hidden state. So these are the key ideas behind the recurrent neural network. It has a hidden state, it has an output, and then it has sort of feeding into itself or to the next layer. That's called RNN. So it's it is a model used in many simple applications, translations, and then language translations, language summary, things like that. But one of the limitations in RNN is that it cannot handle the large context, in the sense long sequence of events or long sequence of inputs coming to that, because it doesn't have any memory of its own. There is no memory, though there is a hidden state. There is no concept of a memory in the RNN. All right, so that's a limitation of RNN. Then there is something called this is a types of RNN. Though in this paper it may not be relevant, but be familiar with all these types of RNN. It's basically one input sequence to input is one, the output is one, and similarly one to many and many to many. So you can imagine you send a sentence and then output is some sentiment, right? That is like many to one. You can imagine many to many is like a language translation. So we have done, I mean, industry has done so many models created out of this. Again, the reason I'm saying here is just to create a foundation for the upcoming topic. Well, and then there is some LSTM. It's a next generation sequence to sequence sort of model. But in this model, you can see that there are elements of some memory. They call cell state, right? So this is very important. In the paper, when we are going to talk about the what we call the memory module, it's called LMM. It has a very similar structure. It's not exactly same, but you can imagine as a foundation, LSTM. It has, in LSTM we have the cell state. That's a memory, and then we have a forget gate, and then we have an input gate and output gate. So this is how you can imagine it is a one sort of unit in the LSTM neural network. So what is the important message or key takeaways from this is to just to realize that in this neural network, we are going to be a hidden state that is called somewhere here. Where is the hidden state? Hidden state is here, right? And then the other thing is called cell state. And more interestingly, there is something called forget gate. So what forget gate is about, this is going to be used in our discussion, is the ability to, change the sort of the memory state. Memory here is a cell state, right? So the forget gate will have the ability to look at the input. It has some learnable neural network, and then based on some conditions, it would be able to forget. That's called the forget gate, and then sigmoid around that. And the input gate essentially creates two things. One, it basically feeds into the cell state. If you look at the diagram here, the input signal is coming from here and going through the sigmoid, and then concatenated with activation function tanh, and then together it becomes a sort of the input to the cell state. That's where it is going here, right? And then output gate, it's combined with output gate, and then finally the output is produced. So that's the idea of the LSTM, sort of the neural one node visualization. All right. Just try to aware at the high level, but when we go to the paper, we will get what exactly we are trying to do. Okay, this is just to get to the equation. A lot of this paper, it has a lot of equations. If we directly look at the paper, you might get a little bit intimidated. Some of us, you look at the equations and all. I'm going to go through the equation, so I'm setting some foundation for that. These are the mathematical notation to explain the neural network, and then to explain how the neural network gets updated. In order to get to understand that equation, we need to a little bit understand the notation here. So these slides help you to understand. So if you look at the forget gate, if you look at this equation, what it says that the input xt, x is an input. Imagine x is a list of tokens. For example, you can imagine some token series. The cat jumped on the moon is the input sequence, right? Or I found the hotel, for example. That is the input sequence. And then xt is input at a point of time t, right? And then what here he is doing is, it's basically the forget is a function of a sigmoid, function of, there is a learnable weight here. WF means, when you see W, that means it's a weight given to some sort of a neural layer. So it's a function of the previous state of hidden state, and then the current input, and then it's basically multiplied, right, or concatenated, multiplied with the weight, that is the learnable parameters in this neural network, and then with some biases, and then the sigmoid applied over that. So that's the way you read this function or equation, right? And then similarly for input gate, it's a little bit more, if you look at that, it's the same way. You can imagine the input IT, is the data created, the new information created, right? Sorry, CT is a new cell or new information or new data created out of activation function, right? And then it's combined with input IT. So this is another way to read this sort of the equation. Output gate is a function of, if you look at here, HT. Basically, output involves two things. When you think about, one is a hidden state output, and then other one is the actual output going out of the neural network to the next node or to the final node. All right. So that's introduction to sort of the equation mathematics to read this paper. So with that, let's think about a little bit about, you know, the architecture of these different networks, right? So these are the comparisons. I think the important thing in my mind right now, look at before we go to the new neural network, let's understand a little bit of comparison between the RNN, LSTM, and transformer, right? I think let's focus on few things here. Handling the long sequence. See, RNN actually struggles with large number of tokens to that, right? Mainly because of vanishing or exploding gradients. What does it means is, as the time goes, as the sequence of input goes, it's not able to keep up the correct prediction. That is a limitation of RNN. LSTM, yes, LSTM is good in the sense because it has now memory. It's able to retain some of the things that needed for predicting or in knowing the past information in the sequence because of the memory attribute. So it's able to do well. But transformer, we know it's though it's not a direct comparison, we know it's anyway better in handling the large sequence of inputs coming in with the different mechanisms. So transformer architecture is completely different from LSTM, but it does definitely do better than LSTM in some instance, right? In terms of parallelization, mostly the RNNs are, if you remember the RNN way they work, you send the input sequence one at a time, right? Similarly, LSTM, you send the input sequence of the tokens one at a time. I think in transformer it's slightly different. But what they are here they're calling parallelization is mainly how how the transformer can update the KQV, the self attention. How does it derive the attention for each of the input vector given to that? It can do it in a parallel manner. So that's a architecture of the transformer. Yeah. So we can skip the other things. The last one is important. Computational complexity. That's a key thing. That's where I want to end here. The paper will start there. What that means is, in the case of RNN LSTM, it's mostly a linear sort of the complexity. But in the case of transformer, it's a quadratic. So you may be wondering why transformer is a quadratic in terms of time complexity and also in terms of the space complexity. That is a key part of the message. And then our paper will go into how we are going to be designing the new neural network to basically to avoid the limitation, right, of the quadratic aspect of the memory and then computational complexity. Okay, let me see the next here. This is just a side information. If you like to know different varieties of RN and LSTM, obviously these are the examples of that. In the case of transformer, there are different types of transformers, right? And then one is the transformer by the Google, explained by the Google paper, and then there are other things like BERT and GPT. With that said, let's go back to our paper. So now we are still in the introduction. If you look at this paper, I'm just going through one by one. The primary building blocks of the transformers, attention modules, function as a associative memory, right? Blocks, where they learn to store key value association and retrieve them by computing the pairwise similarity. Okay, so we have not gone to this yet. So this is a transformer. They are explaining the transformer, what's going on inside the transformer. I tried to convey a little bit in overview, like it has a k in a QKV value, and that's what they are trying to mention here. And then the accurate modeling of the dependency, however, comes with the quadratic time and the memory complexity in terms of the context length. Let me explain that one more time. This is a very key aspect of the paper. And the way I'm going to explain that is a couple of more diagrams. So again, we are a little bit going into the transformer architecture. Here I'm going to explain only in brief. You're again welcome to look at other materials. So what in transformer, the key thing in transformer is, if you remember, if you refresh, basically it's an ability to, transformer architecture has the ability to figure out the attention. That's what they call self-attention. In a given sequence of words, right? If you are at any point of time or input tokens, you want to know how that word or token is related to other tokens in the sequence or in the query or in the input. So how do we find how do we figure out the token that I'm currently focusing on is related to all other tokens? So that we call attention. So for example, in this example, he booked a room at a hotel, right? So let's say that our focus is, what we call target token is booked. Now, how do I know? How do we conclude? The token booked. How is it? In terms of importance, in terms of related to all other words, is what is a foundation of the attention mechanism. See, this is a very simple example. What they, at the end of the day, imagine that there are many over the time, after looking at all examples from the internet or from the source, right? The learnable matrix is called Q, and then K, and then V, is part of the transformer architecture. And then as the input comes in, it's able to figure out the word called blocked is related to hotel with some, here it's a very crude example in the sense number. It has a weightage of 0.3. And then the word called the booked is related to room is about 0.15. So in a simplest word, imagine that imagine that by looking at many different types of documents, which we call training documents, right? You can sense that whenever we see a word called booked, here we, in the sense, let's say the transformer architecture, is able to know the room is, important for me, and then hotel is important for me. So over the time, these KQ vectors, I think value vectors also, together learns this relationship and then able to form the self-attention, by the mechanism called self-attention logic in the transformer. So this is a very, very high level, simple explanation. But what really happening is behind the scene, when the transformer architecture, like GPT, chat GPT, gets the word booked, it goes into the embedding vector. First, there is an embedding vector or input vector for the word booked, right? You can imagine like that. And then it knows that it already have some learned metrics. This is a neural, you can imagine it's a neural network or neural cluster. Through that, it's able to figure out the query vector, right? I'm talking now, it's the inference time or called test time. And the training time is a different, we will talk differently. Imagine right now we are in the inference time, and then this keyword comes in. And then what happens is, in the transform architecture, by looking at the learned weights, it's able to get the query vector, key vector, and the value vector. So that's what this diagram says, right? And after that, it's able to apply is at the end of the day, the goal for the transformer, this attention logic, by looking at the input sequence in our n token for xn, for example, it is needs to create the attention matrix called Z2. In this case, Z2. So this attention matrix or attention vector or attention matrix is what finally will be fed into the next phase of the encoder. If you remember the transform architecture, these attention vectors are passed to the encoders, and then encoders, um, attention is a part of the encoding block, but inside that it passes on to the neural network, right? Forward neural network, fast forward neural network, and then it actually then feed into the decoder. Finally, you are getting the output. But in this at this point of time, our goal is to create this attention vector. So this is how the attention vectors are created. So again, what it does is for the given input vector, it's look at all other query vectors related to other tokens, and then it's able to derive there is an equation I'll show you. It's able to derive apply derive the multiplication of that and apply the softmax. Softmax is basically contained at all the value in the probability distribution, and then it add-ons to the value matrix, and then finally the attention matrix is created. So this diagram can be represented in a little bit simplified way this way, right? Imagine there is a q vector for your input sequence, and then k vector, and then the probability distribution is derived, and then it multiplied with the vector v value vector, and then we get the attention vector. So this is the sort of the simplified equation for that, right? It's a softmax over the q vector, and then k vector ported, and then divide by, it's basically amplification by the dimensions of the matrix, and then concatenate with the v vector. So we don't need to dive into this equation, but imagine these are attention vectors now. All right. So why is that important in our context? Look at this. Think about the context window size here, right? In this case, you can say the context. You see the number of in the context series 4 or 5, right? But in reality, this is just an example. Imagine you have context window of 128K. Think about the matrix size here, right? For 128K tokens, right? You need that many sort of the sized in terms of metrics, and also the computation to do the matrix computation. So all this involves space, and then of course the computational aspect of that. So this is what we call limitations. This is a reason, imagine you need to apply this to so many sessions as well. So this is a reason many LLMs don't go beyond certain limit, 128K input sequence. The 128K tokens comes out of your input that is part of the query, as well as the historical, from your chatbot, for example, if it's a chatbot application, also from other documents you attach, for to derive the knowledge. All right. So that's where we end up in limiting ourselves to 128K or some kind of the limitations enforced on this, attention mechanism. So now this is a serious limitation. The idea behind the paper is to find out, what are the different ways in which we can, right, remove the limitations. So here it says the accurate modeling of dependence, however, comes with the quadratic time and memory complexity in terms of the context length. I think now we all understand why this paper mentions about that. In complex real-world tasks, such as video understanding and then long-term time series forecasting, the context window can become extremely large, making the transformers a challenge in this task. I think we got that by now. We know why, because the matrix computation and size space is going to be extremely go higher and higher as the input context window is higher. To overcome these issues, I think there are various, different types of transformers, also everybody try to approach. One is they try to simplify, if you go back to the mathematical, they try to simplify this by doing what they call kernel function. I won't be going too much into that, but there are attempts to do or reduce the computational complexity of the attention equation using the approach they call kernel functions, right? So in this paper, we don't dive into that, but be aware that there are attempts to do that, improve upon that. All right. And then finally, here they are saying that, now this paper is getting introduced to something called short-term memory, long-term memory. See, when you look at here, this kind of transformer-based architecture, I don't think we see the notion of short-term versus long-term. It's all same here, right? There is no separation here. Whatever the context has, it can have short-term information or long-term information. All of them are into this attention equation or attention, the metrics associated with that. There is no notion of short-term, long-term, things like that. So that is exactly this paper is trying to say. Instead of thinking like that, why not we think a little bit differently? What is it a little bit differently is, somehow the goal is to, though you have a lot of information, right? The historical information or let's say 300 pages of book information in the context. Can we have the ability to summarize, right? The way our long-term memory does, and then provide only the abstract version of that to the attention layer, so that the attention layer is always minimal, it doesn't explode. So that is a foundation of this paper. So instead of thinking as a one matrix, think in terms of two different layers. One layer is responsible for reducing the long term, reducing or providing the abstract information from the long term memory, right? You can imagine the long term memory as a lot of information with a lot of context. But from there, get the abstract information, and then when it comes to the short term, combine with the short term information or short term focus, and make sure this matrix doesn't explode. So how do we design that architecture? So now they are talking about a crucial component. Now they are calling it as a learning process. Now it's called short term and long term and meta memory. And then this paper is going to explain how it's going to work together and ensure in the context window or the attention, the metrics are always limited, still works. That's the idea behind the paper. Now we are jumping to the memory perspective. I think we talked about a little bit of recurrent neural network. And in the RNN, in the plain RNN, there is no memory, right? Though there is a hidden state. But in LSTM, we introduced something called cell state, which is the foundation of the memory. All right, we introduced ourselves on that. And this paper trying to explain, similarly, transformers can be seen as an architecture with a growing memory and two similar steps. So what they are saying is, now I'll introduce the architecture, then I'll come back to this. I have given you good information, and then now I'm going to visually introduce the architecture and then come back to the paper. Okay, so this is the one of the architecture detail in this paper. So this is the same diagram you are going to see in the paper. Now we have some context, right? If you look at this diagram, in this paper there are 2 or 3 variants of this architecture. But let me walk through this architecture. So imagine the attention. The first thing is to note down there is an attention layer here. So first of all, it has 3 layers. Unlike transformer, there is only one attention layer. Imagine in this system we have 3 layers. One is called contextual memory, which is a neural memory. This is what we call long-term memory. You can call it as a long-term memory, right? And another layer here is the core. That is the actual, you can call it as a short-term, right? Our current focus. This is where the input is coming, right? Input sequence are coming. The new knowledge is coming. That is called core layer. And then the another layer is called persistent memory. So in this paper, they divided this architecture into three areas. And then if you look at that, the key learnings, the persistent memory is the simplest architecture. In the right-hand side, it says fixed. What does it mean? That means in none of the persistent memory can be altered or can be changed. It is basically some task-specific knowledge. You can imagine that it's a task-specific knowledge, right? That is always added to the decisions, or in a way the attention will be happening. So the idea here is, this is a this is a fixed memory, and this is the current memory or current focus, and then this is the top level area is a long term memory. I don't know whether they really mapping this to human brain or memory. It's kind of an attempt to do that. So what is that in the long term memory, which is called contextual memory? What's happening is all the information about the past, right? Or you can imagine all the information from a book. You are feeding a big, let's say 500 pages of book into this system, into this architecture. So all the 500 pages of the information tokens will be crystallized or synthesized into this long-term memory. So, you may want to note down the neural memory here we are talking about may be limited in its size. It's not going to grow like our, I don't know, in human memory whether it's limited or not, but the long-term memory or contextual memory is limited with some size. Now, if you feed in a lot of information to the neural memory, it's going to keep the abstract form of that. It's going to keep summarized form of that, right? It's not going to keep all the information. So that's one thing to note down. And then it has the ability to retrieve. That's what this module is about. So what's at the higher level is happening when your new information coming to this system, that's called sequence. What it does is in this architecture, it's going to consult with the long-term memory and then retrieve some information from the long-term memory. At the same time, it's from the persistent memory, some other tokens are added to this, right? That's why you can see the arrow. And then whatever retrieved from the long-term memory is added to the current input. And then along with its own input, all the three things are concatenated together. And it is fed into the attention mechanism, right? This attention mechanism is very similar to what I described in the transformer architecture, right? In other words, and then finally, after the attention is derived, it is fed into, it does not say in this diagram, but essentially it is now, it can work with any neural network, right? It could be transformer, the learned one, the reasoning neural network, in order to derive the in context learning. So in a simple sense, if I have to summarize the whole idea in a single sentence, this is an attempt to do the attention metrics that we did in the regular transformer architecture. Where is the document? Yeah. So in a simple term, what it is trying to do that is it's trying to make sure at the end of the day it's creating the attention metrics. The way it creates attention metrics is different in this architecture. In the transformer architecture, all the inputs that you're giving to the machine is assembled at the time of attention. Okay, but in this architecture, it's not so. Now we get the summary of information from long memory, and then some information from the persistent memory, and then all of them together fed into the attention layer. So the hypothesis is that in this model, the short-term memory, in the sequence of input coming from the core layer, is added with a the abstract information from the neural layer and then passed on to the attention layer, right? And then from the attention layer, imagine it's a, the next step is similar to the transformer architecture, encoders and stuff like that. So that's a key part of this here. And there are now, with that introduction, there are two or three varieties. The different varieties are is easily understandable. But what is the benefit of this architecture again? So if you see that, in order for this architecture to work, I think the key thing is when you get the information from the neural memory, how good is that information, right? The abstract information, right? That is going into the attention layer. So let's think about scenario, right? I mean, when there is a new information coming in, right? And the two things need to happen. So once you use that new information that is in the core layer, you need to go back and update your long-term memory. See, that's what happens in a typical ours in a human-like scenario, right? Whenever we learn some new information, after a while, it goes into the long-term memory, right? It is said that whatever you're learning, whether as a student or any skills, it takes a while, at least some amount of time before it gets transferred from our short-term memory to the long-term memory. I know there are studies, actually the MRI studies, they have actually captured this, from our brain, from our short-term memory, how it's getting transferred into our long-term memory. There are studies, they have done. It actually shows the activity in the brain. So similarly, here, whatever new knowledge we are learning need to be fed back into the neural memory. So one of the approach in this approach called memory as a context, if you look at here, after the attention layer is created, it is again fed into the neural memory, right? And also it's used for our reasoning or for our prediction. But the key thing to note down is the long-term memory gets updated. So that's why you see that arrow mark here. Once the consolidated attention is created, that is fed into some update process, which updates the neural memory. And also, it gets used for the in context learning. So that's the architecture. That's a key architecture we are talking now. Now, let's come up with some example, right? So, for example, let's say you are feeding in a novel, right? It has about 500 pages of documents. And in this paper, of course, paper is more sort of uh, written at a very high level. It does not tell the details of how these memories are updated. But let's imagine that all the 500 pages are being updated into the neural memory. So we can come up with some three examples. One example, as I said, a book example, right? Where as you are feeding in chapter by chapter into this model, into the system, the neural memory, it now has to decide two things. One, it doesn't have enough memory to store all the information as it is, right? It needs to store the abstract version of or important version of the information, and it doesn't want to store repeated information, right? So what it does, what they call, which is I will explain now, and then in the paper we'll walk through that. What they call is a surprise factor. And then there is another concept called forgetting factor. What the surprise factor is about, if you're telling me the same information, right? If the new information you're feeding in, for example, you fed me the first chapter of a novel, right? And then you're doing the second chapter. And in the first chapter, let's say that you're explaining something about that character, right? And some attributes of some qualities of the character. And in the third chapter, again, you are saying the same thing, right? There is no new information about the character. It's the what they call the delta, the difference between the old information and the new information, literally very minimal. So this layer needs to make a decision. Okay, if it's not a surprise, right, and if there is no new information is learned, I don't need to store it. So definitely we need a mechanism to do that. That's called surprise effect. And the other one is forgetting, right? I mean, after a while, in a real human, right, we all know that we may remember some incidents for a long time, but after a while, you slowly start forgetting. Initially, you will forget the details, and then after a while, you will even sometimes forget the whole event. So the forgetting is also another important character for this neural memory. So we are going to mathematically see how we are going to model it. Let me go back to the paper. So what they call in the paper, the memory perspective, we read about that, right? And then I'm going to go down. I explained the Titan. I'm trying to explain the Triton architecture, and then I'm going to a little bit ignore the preliminaries because it's basically a mathematical foundation. But I think if you look at the background, we went through the visual diagram of QKV vector, and here is the output token, and this is the attention equation, and it is the attention matrix how it's formed. Um, and basically it's explaining whatever I explained visually in the form of mathematical notation. And this next one is the attention now using a kernel function. So here, then the quadratic aspect of that is a little bit reduced because they are able to commonize, make a common computation elements out of the attention and then made it as a kernel function. So though it's not a focus of this paper, they explained that here, saying that, we have tried to optimize the quadratic cost by linear transformation. So they're just attempting to say that. And they say even with this approach, they still cannot handle the long context. That's why they are trying to convey in this. Now, what they are saying here is now they are introducing something called M. M is what you can imagine is a memory unit. That's a part of that what you call neural memory. So imagine this neural memory, the cube here, right? Each one of them, imagine that it's a M, right? It has a n number of M a memory unit. So any time at a point of time t, the memory unit mt is a function of the previous the mt minus one and then the new input. I think we verbally said that, right? The new state of the memory is based on two things, right? The new information coming in and the delta between the new and old information. That's what the function is here, right? F means we'll explain the F a little bit detail below, and then the read operation is nothing but how you retrieve the information from the memory. That's they call G. Given a memory and then given the input, you are able to retrieve. So essentially, you need to think about this neural memory has two operations: one retrieval to get the abstract information. Other one is to update. These are the two information, two equations or two operations you need to be knowing. All right, that's about that. Okay, memory modules. Memory has always been one of the core parts of the neural network designs. Yes, we know that. The idea of seeing linear layers as a key value pair. Yeah, this is another important one. What they are saying is, uh, see, in this paper, they don't talk too much detail about what is inside the memory layer, okay, because that may be a secret sauce. They're not talking about that. But what they are saying is, in this paper, each memory has a key value pair. So in the case of LSTM, if you remember, there is a cell state, right? Here, it is not explicitly said, right, about the cell state. But what they mention in the paper, each memory has a key value pair, very similar to, in a, in a, it's very similar to what we know in the case of semantic search, right? And then also in the transformer, we have the key value pair. It is in the same concept. They associate key value pair. Again, whenever you think about key value pair, it is always a learnable, right? Weight parameters are there. So it is a little bit of mini architecture, key value pair architecture inside the memory, but they don't go too much detail inside that. They stayed at the very high level in this paper. Okay. So now learning to memorize at test time. Okay, now we are getting into the details. Now having known about this one of the architecture, I will explain the other architecture, variants of the architecture. But having explained the one architecture, they are explaining, learning to memorize at test time. So why is it called memorize at test time, right? So usually, test time means, during the inference time. That's what it means. During the, that's another way to sort of understand that. So here, what's happening in the example we are mentioning, right? In this example I was mentioning is a book with the 300 pages are fed into the neural memory, and then we are asking some questions to that. You can ask, what is his character did? What are the qualities of the character? Right? Something, tell me the events. So those are all the inference time or test time. That's why during that time, um, so not only questions, now you are fed about 30 chapters, and then 31st chapter, right? You're feeding the 31st chapter into the system. And then at the time, the neural memory will get updated, right? Because the new information may be there, new surprise may be there in the input. So they call it as a test time, learning to memorize. So now what we are saying here is memorization, however, had almost been known as undesirable phenomena in the neural networks, as it limits the model generalization. Well, yeah, I mean, this is what they say is, yeah, exactly. This is good. This is a good information. So the previous design of LLM never had any memorization, though they had reasoning, but they never had memorization, right? Because memorization is always thought as it does not generalize, it will overfit. So that's the reason these neural networks obviously don't have this concept of memorization. That's why they call it as it's undesirable phenomena in neural networks. But interestingly, now we are combining the memorization for our own benefit, for information, knowledge abstraction, and then combining, obviously, after that tension, you have that transformer like architecture. Okay, we argue that we need an online meta model that learns how to memorize, forget the data at the test time. In this setup, the model is learning a function that's capable of memorization, but it's not overfitting the training data. Well, that's a key. That's interesting. How it's happening? Of course, now you know that, because we know there is a clear separation of memory and then actual reasoning happening after this layer, right? The actual reasoning with the neural network happening in the attention layer. So that's together says that this statement makes sense to me. What we are doing now we are basically trying to model. See, when we try to understand a new system, right? We always try to understand visually. This is a visual representation, and then we try to understand intuitively, right? Intuitively, we are trying to see how the attention matrix is feeding into transformer, and then why this architecture makes sense. Obviously, the third aspect is the mathematical. So this is a mathematical way of understanding. So what they are saying is the memory at any point of time t is is a is a function, right? Is basically based on the previous state of that memory. Again, memory, imagine, memory is a key value pair, right, of the input sequence or the document sequences. And the new state of memory is based on how much surprise happened between the previous state, mt minus 1, and the new input sequence. And then what is a delta? What's the delta loss? Is it two completely different between the previously you said about something versus now you are saying about this similar thing? So how completely it's different? If it is not much different, then the surprise element is 0, right? But if there is a surprise element is higher, then this memory is updated correspondingly with that. So that's what this equation is trying to convey. Okay, fine. And then what they are saying is, they can further a little bit clarify the surprise element is a little bit more complicated. It involves multiple components. One is what they call momentary surprise, and one is called past surprise. So this is an example of human. Maybe it resembles a human mind. So, for example, even in the novel example I said, right, if you're talking about a character in the same thing, the character likes this. After the third or fourth chapter, you're saying the same thing. There is no surprise thing about the character. On the other hand, if you convey new information about the character or the hero, then that's a surprise. then the delta is more. Then the memory system would able to remember that new surprise information. So that is the momentary surprise. And then and the past surprise has two things associated with that. um, as the time goes, right, even the past surprises, if the has to have some decay factor in that, right. That is where this is a part of the decay factor, what they call any knowledge or any surprise over the time. If there is no first of all, if there is no delta, it's not going to be a new surprise. And uh, and also any surprise over the time will have some decay factor. So that's what this is eta t about. So that's the equation. I mean, though they didn't mention it in, of course, you cannot say it in the diagram, but that's what the equation is about. So how this is actually coded and all, that's a different thing. This first of all, this paper is just a research paper, right? It's probably not in any of the Google's products. We are assuming, we can assume that in a future, if it's a successful idea, many products might have that. And I think I saw somewhere in the announcement that they will share they'll share more about this paper, perhaps some samples and examples in the. All right, so that's a key thing. Now what is going on in the memory module, right? Two aspects. One is how it handles the surprise, how it handles the decay of the knowledge. Again, why it is important, because we don't have unlimited memory. We have only limited memory. Within the limited memory, we need to forget some things, right? We need to abstract something. We should ignore something. All the things need to happen. So this abstraction, this equation is trying to convey that. Okay, I'm going to just a little bit ignore. Yeah, I think this is exactly the way I was mentioning. But I mean, I have given you the foundation. So okay, I might have a little bit misaligned, or so the foundation, the forgetting aspect is this one minus uh, alpha t, I guess. So this is a foundation aspect, and then this is part of the surprise aspect. Okay, we are coming here, and then the retrieving memory. That's very straightforward. As you can imagine, the retrieving happens based on the query vector that you provide q, and then based on the memory, right? Obviously you can imagine that every m module has a learned weights as well as the q vector, right? And k vector. So based on that, it's basically decides the retrieval mechanism. It's not exactly same as the transformer retrieval mechanism, but there is a function they mentioned. There is a retrieval mechanism. It basically takes the m, and then m is the memory in which key value pairs are there, and then based on the q vector, it's able to give you the y. Okay, this is very good information. What they say, what they really talked about the long-term memory now, right? And then in pictorially, visually, we also talked about the long-term memory. Then now this is called memory as a context architecture. Okay, and let's talk about other architecture. So you can think other architecture is a slightly variant of this architecture, right? It's very simple. In our next architecture, it's called memory as a gate. So what do you see? From this diagram, you can visualize that there is no update happening to the memory, right? In the previous architecture, there is the output of the attention is fed into. In other words, new information is fed back into the memory. So actually, so though yeah. So there are two things happening. One is updating the sort of the memory weights and stuff like that. Other one is compression. So neural memory has, there are two kinds of write operation, or two kinds of update operation. One, because it is a LSTM like model, any input sequence comes to that LSTM will have its own what we call cell update, right? And then few updates on that. That's one type of update. The another type of update is like you want to really update some of the attention metrics, and then update the weight and the learnable weights. That's another type of update. So in the first architecture, you have both. One is through the in the input coming in, the new information is absorbed into the neural memory, as well as the output from the attention also fed into the neural memory. That's the first architecture. In the second architecture, the output from the attention is not fed into the neural memory. Rather, right, only the information coming from the input sequence and from the persistent memory are fed into the long-term memory to to add into the long-term memory. You can visualize like that. So that is all the difference between the previous architecture and this architecture. Okay, you can ask me, what's the benefit of this architecture, right? That's more of intuition and more of a trial and experiment. And they found out, these different architecture works, perform differently in a different situation. Um, Maybe over the time they may have an intuitive way of explaining that. It's more of an experimental explanation. But this is the mechanism of the second experiment or second architecture. And then third architecture is what they call memory as a layer. In this case, which is slightly different from the second architecture. Again, the input from the long-term persistence and then input sequence are fed into the long-term memory. From there, the whole abstraction is fed into attention. I think this is the simplest architecture, right? And both input is fed into the long-term memory, whatever currently, let's say we are coming, the current as it is happening is joined with some persistent memory and then fed into the long-term memory. And then from there, the abstraction comes out and then fed into attention. So it's a slight variation. So this is called memory as a layer, right? So now let's think about the intuition, right? Um, so why this architecture works on different contexts? We'll look at the results and then we can explore why it does so. But for now, just imagine that there are three architecture, and then there is a fourth architecture. They didn't put it as a number. What they said is without the persistent memory, if you have simply the neural model memory, they are calling it as a fourth architecture. In the paper they didn't put it directly, but in the results section they mentioned as a LMM as one of the fourth architecture. So when we look at the result, we will talk about. I think we talked about key things behind the memory architecture, right? Yeah. I mean, rest of them is going to be very straightforward because this paper is once you understand the first concept, the rest of the concepts are very similar. The equations are very similar. There is nothing. It's a no-brainer. For example, in the persistent memory. We talked about the persistent memory. The paper simply says that it's if you look at here, it's the learnable data independent weights. There is no clear example of um, persistent memory given in this paper. They simply said it can be task specific weights your system has from the beginning. I don't know what that means. It could be for depending upon your use case or depending upon where you intend to deploy. There are some task specific weights that need to be always attached to the input, the core, the input coming to the core, that they call it as a task specific. So it's easily modeled. If you look at the equation, what they're saying is all the information coming from P1 to P, the P means persistent, P1 to P and P is concatenated with X. And that means you can imagine this diagram, right? This is concatenated with X. All this information, this way, these input tokens are merged with the input sequence. That's what this equation is. The new X is formed. And there is one thing I missed to communicate is the sliding window. What they are saying is, you know, when you form this, when you assemble this new input sequence, okay, how are you assembling this? Some of them are from the persistent memory, some of them are from long-term memory, some of them from the sequence, that the current sequence. You are assembling this and you are feeding into the attention layer, right? So when you are assembling that, sometimes you want to go in a sliding window. In other words, don't feed all the information into the attention layer, but go in a sliding window. That's another variant of this approach. So they identified the when you go through a sliding window, they can ensure that attention is, of course, not exploded in terms of the size and complexity. And also they feel that, they demonstrated that the perplexity, what they call ppl, that's a evaluation parameter for remembering the past, is better in some situations. So when in the paper they will explain, when you go into the memory as a gate. Oh, another thing, memory as a gate approach, they are suggesting the sliding window approach. And also the gate here means you haven't, there is an opportunity, there is an option for the system to decide how much, how much should I give weightage between the information coming from the attention layer and between the information from the neural memory layer. So this architecture, if you look at this architecture, the information from the neural layer, long term, when I say neural layer, long term memory, is not fed into the attention. Have you noticed that, right? In the first case, information from the neural layer is fed into the attention. In the second case, the information from the neural layer is not fed into the attention. It's rather concatenated with some gate. You can decide here what percentage of, right, the information coming from long-term memory. I'm just giving some crude example. Oh, I want to consider 50-60% from long-term memory, and then 30-40% from the attention from the short-term memory. You can say that. So that's what the concatenation gating means. So you can decide how you want to concatenate and then send it to the in context layer. Okay, so now we have said that there are 3 or 4 varieties. Now think about how it applies to your situation. Now let us think about the RAG implementation. So now, for example, how in the case of RAG, when you have a so first of all, the question comes, in this architecture, if this architecture is a reality, do we still need RAG? Right, that's a question. The answer is we still need RAG. Why? Um, See, even though it is definitely better than for example 128K context, right? 120K tokens. If you think about the RAG is much more bigger, right? And then the RAG is needed for multiple reasoning. One, to get the context. So RAG maintains the detail, not like abstract version of the neural memory. RAG maintains much more detailed information about the past or about the context. And then, right, and then it might be needed for different situations differently. So the question of whether we still need RAG versus we can be still with the neural memory is an interesting question. But we still think that, even though with the neural memory will come in, as part of the system, that is, remember, this neural memory is sitting in the inference engine, right? Not in the client side, not in the RAG side. I believe we still need RAG. And the second question is, yeah, there are many RAG technologies now, right? In terms of, if you think about in RAG, things like hierarchical summary, you can visualize the same, information with a large data can be summarized in a hierarchical fashion. And then there are techniques like Raptor, which keeps summary of summary in a hierarchical way in the RAG. Is that provide a very similar architecture, right? Is it provide the same benefit? In other words, you control in the RAG side, the amount of context that can be derived and then sent to the LLM. Is it same as the neural memory, right? Having the ability to summarize. Well, I don't know the answer, but neural memory architecture has still more functionality. It has a, if you think about it, it has a It has a forgetting mechanism. It has a surprise understanding mechanism. So those are the things we don't have it in the RAG as of today. But you can ask the question, why not? Why not we take the neural memory sort of implementation in the RAG side and see. So that's outside the scope of this paper or discussion, but just a thought comes to my mind. Okay, so I'm just going to go down the paper. Let me pause here, and then I'll ask some questions, and then I'll continue to the results.
This attention mechanism is working, right? The same way, like how the forget it is working, like is I just want to understand that. So is
Yeah,
there any chances like how it is forgetting because it's under okay because of this a cat sat on the mat, then it's immediately saying okay mat is the thing and it's under, based on the context is attention is going. Similarly, how the forget mechanism is working. Just want to understand that. Is there any mechanism for that to
yeah,
forget?
good point. So let's look at the equation, and then yeah, forgetting, right? So idea is, if the information is not needed anymore, what does it mean? So one I'm thinking, one in the subsequent one, there is no surprise, and then second is, if the information is not asked by future, right, or referred by the future tokens coming in. And then, but that is not the criteria. That also there is an element of decay. They just simply said decay. If you look at the equation, the decay is 1 minus alpha, right? So they didn't go into detail, but when we generally talk about decay, we generally talk time, right? As the time goes, we forget. That's a human behavior. But that's a good question. There is no further detail here. They left it at that point. Yeah. So some kind of decay. That's all we know at this point. Yeah.
Question, Krishnan.
Yeah.
Uh, what was not apparent to me is
Hmm.
what is stored in the long-term memory,
Okay.
the top line.
Yeah.
Is it the hidden state or the attention value?
Yeah.
What number is stored there?
Yeah.
Yeah.
So it's a key value. What they say, for example, this is what they say. It is like, let's say the input sequence, right?
Mm.
Let's say a chapter in the book is fed into that long-term memory, right? The chapter has a lot of tokens, right?
Mm-hmm.
These tokens, imagine there is a key value and then k value and kv value, right?
KQV.
So
Yeah.
that is if yeah, that is nothing but two matrices. You can imagine k matrix and value matrix.
Yep.
And then what is a k matrix and value matrix? It is again now they didn't go into detail. It's again a neural learnable weight there, not neural network.
Mm-hmm.
It's a matrix. It knows attention. It's kind of attention. What is the most key aspect of that inputs or tokens? What is the value aspect of the tokens? So, in a simple word, imagine from the text we are feeding in, they are creating two matrices, k matrices and value matrices.
Mm-hmm.
So, in other words, you want to know what are the key tokens. You have, let's say, 100-word sentence, right? In the 100-word sentence, there are key words which is very important, like verbs and
Yeah,
nouns.
there are probability higher.
A
Yeah,
probability
the
higher.
weights are
It
higher.
doesn't
Okay.
need to know art D and A and all. It may not need to
Mm-hmm.
remember. So I'm just making up. It's
Mm-hmm.
not crude. It's a crude example. So it knows what are the important letters or important tokens from the paragraph, and that becomes embedded into the key and value matrix. So we can think like that. The memory unit consists of key and value matrix. It knows what are the key important information from the sentences. Is that making sense?
And reflecting. So
Yeah.
what? Say, let's take an attention, a transformer.
Yeah.
Initially, the long-term person memory is empty,
Yeah.
right? When you start,
Mm-hmm.
right? As you start feeding queries,
Mm-hmm.
now you go through the KQV vectors, all the learning, right?
No, you're talking the transform architecture or here?
In the transformer,
Okay.
even here, right?
Here also. Here
Here
also.
also,
Correct.
you go through a KQV
Yeah.
vector. Initially, the memory is clean.
Yeah.
Nothing is there
Yeah.
in the neural memory.
Mm-hmm.
Now you have there are what you feed there can be you can take the H vector for each of the tokens and put it there,
Mm-hmm.
right? There is more context, or you can take the whole attention. It's a summary of everything, right? Of the whole paragraph.
Yeah, here in the learnable, in the
Uh,
case of neural memory, they are not calling it as an attention.
mhm. They're actually
Attention
putting
is
the tokens.
here.
The
It's
most
only,
important tokens are
yeah.
put back there.
Yeah. Here they are not saying that. In the neural memory, there is nothing called attention.
Uh,
It is only the uh, key and value memory. There is no attention equation or attention logic is there. All attention is happening later. So here
ah,
just a simple representation of the words key value of
so
the
they're
input.
taking the important key and uh,
The reason is
uh,
exactly I think they may need it to know what to forget and what to summarize, right? That for that reason, not for attention reason, just for the reason they need to forget something, right? And then they need to so that the inner space is used.
Uh,
And
I can paraphrase.
yeah,
I think I agree with you. You don't need to retain attention. Attention comes
yeah,
only when you are answering a new token,
exactly.
new sequence,
Yes,
right?
yes,
You don't
yes,
need attention in the
yes,
beginning.
yes,
So what you store is as sequences of queries are going through,
right.
you retain the most important key K and V vectors.
Absolutely, yes.
That's all you
That's
retain.
all. Yes, exactly.
And next time when you go through this, you retrieve when a new token comes in,
Right.
you go there and pick up whatever is in the k nearest neighbor or whatever more relevant,
Mm-hmm.
right?
Mm-hmm.
You pull that back in and add it into the in this example,
Yeah.
concatenate. So that means more relevant text is there, and now that becomes the whole bigger. You're exactly expanding the context window in a way.
Not I mean, I won't say expanding the context window. So i-
Because from the memory, you're adding to the context.
yeah, yeah, but yeah, that is true. From the memory, once you get the information, you are
Yes,
adding to the context. Let's say this is a context window.
yes,
Okay,
yes.
I'm just moving my cursor.
Yep,
That is
yep.
called the context window.
Yeah, you're
Yeah,
adding context to it.
correct.
Yes, yes.
Okay, you're right.
Got it.
Yeah,
Yeah, that's primarily what I think that is the essence of this paper for me.
yeah,
Okay,
yeah.
because what you put in to that persistent top layer, right?
Right.
That is the core of Titan, and there is element of the bottom layer. Is it
Yeah,
called persistent memory? And you showed the logic.
correct.
So if it is, I think no. So second point is more than RAG.
Mm-hmm.
This is kind of impacting the whole agentic mechanism, right? In agentic, you need to have memory,
Yeah,
and
but
you
yeah.
and you also need to have a reflection on it.
Mm-hmm.
Memory plus reflection, right? So as queries are going, if it is summarizing, I don't think it summarizes here. It is just retaining the key tokens, right?
I mean, that is true. The summarization is not talked now. After
Okay,
the attention, right, all the information fed into the in context learning, where it can be summarized as per your NLP needs.
got it, got it.
Um,
Thank you. I think I wanted to know what was stored. K and V.
correct.
Okay,
So
correct.
yes, basically K and V. Yes, that's what it's stored. The actual mechanism of, there are many questions like
I
how
have
does
two.
it? Yeah. Sorry.
I have two scenarios to ask.
Yes.
The first scenario is, for example, let's say that regarding that contextual memory, say that I have studied in a group of with a group of people, and I met a person long time ago.
Hmm.
For example, let's say Julia, my classmate. I haven't spoken to her. I haven't heard anything about her for a long time. Does it mean that the contextual memory will forget that particular name?
Yes, that is called surprise factor. Yes, there is a what they call in the paper. There is a surprise factor. They did not explain what is the surprise factor behind. So they have given example. If you go look at the equation here. So most important thing is this equation. When you're see if you're not feeding any new information to the long term memory, nothing happens, right? Uh, there is nothing. Let's imagine they are only retrieving. There is no information in your feeding to the long term memory. Apparently nothing will happen except the decay factor, right? If the decay is based on the time, some information will be lost. But your question is, if the if you're feeding some new information to the long-term memory, then it's always compared. It has an ability to find out the new information is, which part of the memory it is related to that, and then is there any surprise? Is there any new information about that key value pair I was talking? So though they did not go detailing, this is what they mentioned. This a delta with the difference between the old information and which is already in the memory versus the new information is no surprise. That means we are talking in a verbal way, no surprise. And mathematically, it could be the difference of key value summation with one part of the memory structure with new information coming in. So they're not detailed out in the paper. Those are all next level details. So for at our level or at high level, they claiming that if the new information is no different from previously stored information, then surprise is actually less. That's what they are saying. In which case, the memory will not be updated. That's sort of the equation they are proposing. Is that answer your question?
Okay. Yeah. Yeah. Yeah.
Yeah.
Uh,
Unfortunately, they didn't go further detail in this paper.
oh,
I think, yeah, right. So you
okay.
see that,
Nice.
yeah.
Yeah.
If you read this again, you'll definitely get to fully understand this
That's
part of the paper.
okay.
Equation 8, equation 8 is the key thing.
Thank you.
All right. Thank you. So I'm just going to wind up by looking at the sort of the results. Let's go to the results. Okay. So what they did is, the key thing for to understand the results. If you look at here, there are four architecture. We talked about memory as a context. The one I first explained, memory as a gateway and memory as a layer, right? And then LLM is the one they didn't put it as a separate diagram, but you can imagine, that is uh, without the persistent memory, right? So idea here is they have two types of performance. So one thing I noted down, if you the perplexity is a evaluation matrix. The lower the number, the better the predictability of the LLM in term when there is a large context. So you can easily say that compared to other architecture which is in 40s, 49, 43, we are talking about in the range of 29, 28. So it's a significant, it's definitely like 20 to 30% improvement. So perplexity is key thing. And in terms of the accuracy is accuracy is doesn't mean it's for the large context. It generally it's how accurate is the reasoning capability. I think it's close, not much difference. But perplexity evaluation is what determines this. How the LLMs can handle the large context. So it's definitely they have improved 20 to 30%. So that's a claim. Again, they have stats on smaller parameter model, 340, and then 400 million model, and then 700 million model, right? So they are consistently showing that the PPL perplexity is, well, in this case, okay. I think as the model size is increasing, I'm seeing that, for example, in 760 million parameter model, it's not. It is I think the difference is less compared to the 340 million parameter model. So, but anyway, whatever it is an improvement. I mean, that is why this research goes right. Initially, they know there is really a good value, and then they keep improving it. Hopefully, if this architecture is good, you would see more and more better uh, numbers in this. And then another diagram you want to see, that is, if you look at this diagram, the one that is in the red color is a Titan, memory as a context. And as the sequence length is increasing, and they are still able to maintain the accuracy in the 80, 70 range. But other architectures, going down. So if you can see, I don't know what color is Mamba is this color. So you can see the red color is the Titans. It's still in the top. Um, so that's kind of the metrics, and I don't know much about this benchmark. Baby long benchmark. Okay, so I'm not sure what it means. So I encourage you to read these things, but let me pause here, right? And then we will conclude here by saying that in this paper we present a neural long-term memory that, as a meta and context learner, learns to memorize at test time. The neural memory module is a recurrent model in nature. and is adaptively memorizing tokens that are more surprising or close to the surprising tokens. Okay, that's that is important thing. What they're saying is if there are new incoming information is surprising, it's surprisingly adapting to that nicely. That's what it says. Comparing to modern recurrent models, it has more expressive memory update and storing mechanism. Using this memory, we present Titan's architecture and its three variants, in which we suggest to incorporate the memory module as a context, gating, and then layer. Our experimental evaluation on diverse tasks and validate that Titans are more effective than transformers and recent modern linear network models, that is, the kernel models, specifically for long context. That is, Titans can scale to larger than 2 million context window size. I see. And that's the conclusion. Titans are implemented in PyTorch and JAX, and we intend to make the code we use to train and evaluate a model available soon. Yeah. Hopefully, once it is announced or once it's released, we will meet again and then run the code. All right. Okay, then.